Tutorial. Today we want to look at real number system. This is the second part. Last time we looked at the real number system part 1. If you have not looked at that, kindly look at the previous tutorial you have there. So if you have not subscribed to this channel, kindly subscribe and share it with your friends. Welcome to the continuation of real number system. So we are looking today with the numbers called rational numbers. This is a subdivision of real numbers. Rational numbers. Rational numbers are noted by that Q. The number m of n, or a fraction of m and n, where m is the numerator and the n denominator, where both are integers, and making sure that n is not equal to 0. So if you find this kind of number, that number will be called rational number. In this case, m and n have a GCD of 1, which implies that m and n are relatively prime. So for a number to be a rational number, the denominator and the GCD of denominator and the numerator should have a GCD of 1. So it's a relatively prime. Such a number, we call it rational number. A rational number. Okay, properties of rational number. So a rational number includes all integers, and also it will include both terminating and recurring numbers. Okay. Again, if a number is not rational, then that number is irrational. So the complement set of rational number is irrational numbers. And these are rational numbers which neither recur or terminate. For example, if you have a root of a prime, a square root of a prime number, this number does not recur, neither terminate. This number will not give you the GCD of 1. GCD is not 1. Again, pi and exponential. Those are commonly rational numbers that we normally meet in our discussions. The other numbers are called algebraic numbers. Algebraic numbers. And algebraic numbers come from polynomials. These are basically roots of polynomials. And a polynomial generally looks like that, which will be equal to 0, whereby an is not equal to 0. So these a0, a1 to an are integers, and they will make roots of the polynomial. These roots of polynomial are called algebraic numbers. They are algebraic numbers. Remember what we are saying. We are saying these are integers, and these integers are roots of the polynomial. And these polynomials now are these roots, which are integers, are giving us what we call algebraic numbers. But remember that all algebraic numbers are not integers. So that's the reason we are saying the converse is not true. It's not true. So kindly subscribe to this channel so that every time we post anything here, any tutorial, you are the first one to get notification. Remember, this is introduction to real analysis. So let's look at an example here. Root 2 is an algebraic number, but it's not rational. So that's the reason we are saying not all rational numbers are algebraic, but algebraic numbers are rational. Okay. So rational roots theorem. Let's look at rational roots theorem. So if we have R, which is equal to this, and that's the definition of rational number, having a relative prime, both numerator and denominator, GCD, relative prime, and R is the root of the polynomial, and R being the root of polynomial. Now this becomes a definition for algebraic roots of the polynomial, and this is the polynomial where this is true, and defined for n is greater or equal to 1. Then in this case, P, which is our numerator, defines a naught, and the Q, which is our denominator, defines an. So that's its rational root theorem. That's how it defines it states. Okay, that the numerator we will define a naught, and the denominator we will define a rational roots theorem. Okay. Let's look at this. To show that 6 power that is not rational, we determine the possible rational roots for a polynomial. The polynomial that will give us this as a root is actually this. Because if you solve this, it will give you equal to 6. That means x will be equal to 6 power that. So that this is now the polynomial that gives us this root, at the root of this. Hence, from here you can see an is actually 1. You see 1. Then again we can see a naught is actually this one. That is a naught. So that the only possible rational roots for this are using the idea of dividing, that the numerator should divide a naught, and the denominator should divide a n, which is 1. You'll find these are the possible rational roots. So these are the only possible rational roots, which will mean what? It will mean that 6 power that is not rational. It's not rational. Because the only rational roots that you can get are actually these ones, applying the rational roots theorem. Okay. Let's look at this theorem. Let P be a prime number, then the root of P is not rational. The root of P is not rational. Now let's see how we can prove this. And for us to prove this, we use a contradiction method. So we prove by contradiction. We assume that root P is rational. Then we can write root P as far as the rational. Definition of rational is what? A rational number can be written in form of m over n, where m and n are relatively prime. And remember, m and n are integers. So if you square this becomes true. Rearranging or make m subject to the formula, we come up with first equation. We keep it there. Then next, that will imply what? It will imply that m squared is a multiple of p because it's n squared prime. Okay, there's a multiple of p. How many times? P times. So m squared is a multiple of p. Then since p is prime, it will imply also that m is also prime. Because m squared, as far as m squared is prime, then it means m itself, which is not squared, the square root of m squared is also prime. Say for example, m is a multiple of this, so m is lambda p, and we call that one second equation. Because we have introduced lambda, again lambda is a multiple of, is a member of, is an integer. Okay, with that, let's just solve the two equations and try to equate what can be equated. So you find that m squared, you imply that that's true, and this is originally that was true. Okay, that will imply what? N squared is actually that, implying what? Imply that n squared is also a multiple of p. How many times? Lambda squared. Which will mean what? It will mean again that n is also a multiple of p. But what do we know about rational number? They must be relatively prime, which will mean that it's not true in our case, because the two m and n are multiples of the prime. So that means they will not be having a GCD of 1, and hence that becomes a contradiction, and therefore root of p will not be a rational number. And end of the proof. End of the proof. End of the proof. If you have a question on how you play with this, you can leave a comment. I'll show you how we do it. Okay, kindly subscribe if you have not yet subscribed, if you are new in this channel. Okay, next, even and odd numbers. We have also even and odd numbers. If you have m, which is an integer, then we define even if we say m is even if is 2n. For n also, n being an integer. And if it's odd, if now we have m, it will be 2n plus 1. That one will be odd. 2n plus 1. Even 2n and odd 2n plus 1. 2n plus 1. Okay, theorem. Let's look at a theorem. The square of a real even integer is even, and square is even, and the square of odd integer is odd. Okay, basically look at the square of real even integer is even. So let's take one of real even, like 2. Okay, square it. You get 4. You get 4. Okay, so it's 4. 4 is even. Let's take 3. 3 is odd. Square. What do you get? 9. 9 is odd. That's basically what the theorem is saying. So let's try to prove the theory. So we let m, by definition, be an integer, which should be even. If it's even, m will be equal to 2n. For n, again an integer. As if we square this, we square m, because you know the square of it will be also be even. That's what we want to show. So m squared equal to 4 squared by definition should be 2 times something times n, and therefore that's the reason we are breaking it to this. And that implies what? Since n squared is an integer, it will imply that again n square is even. Part 1 proved. Next, for odd, if you let n to be an integer, for odd we know that n will be equal to m plus 1. Okay, and m is integer, of course, so that n squared will be equal to 2m plus 1 square. And you try to rearrange, when you expand this, try to rearrange group, you'll find this is true. So assuming 2m squared plus 2m squared is being m, you find that it gives us the pure definition of odd, and that means that a square of odd number is also odd. End of the proof. End of proof. Okay, so if you have not subscribed yet, kindly subscribe. If you are the first time here, kindly share with your friends so that they will be able to get this information. I will be giving you various topics. This is Introduction to Real Analysis. Bye for now.